All right, folks. Well, I want to talk a little bit about Lab 3, where we get into this idea of using let-over-labels-over-lambda to try and create a class-like interface in Lisp. So again, what we're doing is building and returning a function that has some kind of stored internal data state and allows us to provide essentially dispatch commands to this function to say, okay, do this to the stored data state that you have. So again, this gives us very much like a kind of class and method-like access to some kind of stored internal data. So what we're going to do for this is based on one of the examples that we pulled out of the lecture cases that we did, where we looked at time dilation. So if you've got two different entities and one's traveling much faster than the other, or at least at a relative speed much faster than the other, then time appears to pass slower for the one that's traveling fast. So you can actually calculate what the difference is, and that's what we're going to do here. So we're going to say we've got a home planet somewhere that we'll treat as kind of our stationary base, so all the speeds are measured relative to that. So we've got this home planet, a whole bunch of spacecraft take off, all traveling at different speeds, and so time is appearing to pass differently for each. And what we want to do is to be able to say, well, over the course of time, we'll keep track of how much time has passed on the home planet, and we'll keep track of changes in speed for all these different spacecraft, and try and keep track of what time it appears to be for each of them. So we're going to have our dispatch function allows you to give commands to say, well, what time is it back on the home planet? To change the current speed of any of the given craft, to change how much time has passed on the home planet. Say, okay, well, you know, another 1,000 seconds or 1,000 years or whatever your time unit is has passed on the home planet, and then be able to go off and update how much time has passed for all of those different craft. And to be able to look up, okay, well, what time is it now on any given one of these spacecraft? So this is the idea. Obviously, this is a much more involved lab than some of the ones that we've tackled so far. And what I want to do is run through the functionality that I want you to provide for this. Once we've gone through that, then I'll also throw in a couple of requirements for implementing macros for this to give the user kind of a shorthand way to invoke commands on this dispatch function that we're creating. So there's the plan. Again, usual idea, so this is Lab 3. It'll be in a Git repository called Lab 3 that you'll be forking and cloning. The due date for this one, if I recall correctly, is February 25th, so you've got kind of 2 weeks of class time plus the week of the break to work on this one. And again, it is a little more involved than some of the ones we've done previously, so I would advise, you know, starting early so you can take a couple of stabs at this one. I am going to run through the approach that I took in developing a sample solution to give you kind of a guideline on what I think would be a reasonable approach. So when you grab your repository, it's going to have a skeletal version of the build time tracker function. So this is the function that's going to create and return a dispatch function that the user can then work with to go off and, you know, set up their spacecraft and figure out what time it is for everybody. So the syntax for calling build time tracker, so when somebody actually wants to use this function that you're creating, they'll call build time tracker, they'll give it a name for the home planet. I'm using Fred as the name of my planet and Bob and Joe as the name of a couple of the spacecraft here. So you've got a name for your home planet as a string first, and then a whole bunch of pairs, and each pair represents the information for one of the spacecraft. So it gives the spacecraft a name, and it gives the spacecraft a speed. And the speed, let's say, is being measured in kilometers per second. So 10 kilometers per second for one and 23 kilometers per second for the other. So you've got this list of the initial name for the home planet and then a list of pairs for all the spacecraft that you're going to be keeping track of. And again, so the names have got to be strings, and the numeric values have to be non-negative integers, so 0 or greater. All right, so this build time tracker is returning one of these dispatch functions that we can then use to issue our queries and issue our updates. So as we're going through, we'll say there's a variety of different commands that the user can issue. So they can, query speed, query time. So here are some of the examples of how this would work. If we called build time tracker and stored the dispatch function that it returns in a variable, I'm just going to assume it's stored here in a variable called dispatcher. So we did something like def-var dispatcher and then called build time tracker with our list of arguments. Now we're going to start issuing commands to the dispatcher to say, okay, well, I want to change the speed of spacecraft Bob to 2500. Or I want to look up what the current time is for Bob. So on the dispatcher, I pass current time. So I'm running the dispatcher function on arguments current time and Bob. So this is looking up what the current time is for Bob. If I want to change how much time has passed on the home planet, I specify time passed and the additional amount of time. So this is on top of whatever time has already passed so far. Right? So these are the kind of core commands that we'll want to implement as part of the dispatch function that we wind up returning. And again, this is going to be based very much on the same style of let-over-lambda or let-over-labels-over-lambda construction that we looked at in our lecture examples. The other thing, of course, that you'll need to know is how to actually compute the time based on how much time has passed on the home planet and how fast the spacecraft is traveling. So this is the, if I haven't messed it up, this is the great ugly formula for going through and figuring out the relative time. So n is the amount of time that has passed on the home planet, or for the time period that we're interested in, and s is the speed that the spacecraft is traveling at, and c is the speed of light. And we're going to use this constant as our speed of light. So whatever, 299,792 kilometers per second. So that is kind of the core aspect of what we're trying to set up. So as an example again, if I was going to, in this case I'm going to use TT as the variable that holds the dispatch function that gets created. So I say, okay, I'm going to run def-var TT and then call this build time tracker and tell it, okay, Max is the name of the home planet, and then I give a bunch of pairs. And then I can go through and say, okay, well, let's look up how much, or pardon me, let's set how much time has passed. Let's add 1,000 seconds to the time that's passed on the home planet. So I run a fun call on that dispatcher, specify a new amount of time or an additional amount of time has passed. It's 1,000. I can go through and look up. So I'm just using R to keep track of whatever these functions return or function calls return. Now I'm going to say, okay, well, based on that, what's the current time for the Emma spacecraft? Or go through and let's change the speed of the Zalika spacecraft. So we're just going to go through this process of, over and over and over again, issuing new commands. So whatever's happening here, right, when we introduce a new amount of time passed on Earth, of course, that's going to introduce new amounts of times passed on each of the different spacecraft that we're going to have to go off and carry out. So the skeletal version that you're given is, again, just following that let-over-labels-over-lambda construct. So the lambda piece at the end is the dispatch function that you're returning. The labels allows you to declare a collection of local methods that your dispatcher can make use of. And again, it just makes the code a little easier to follow. And then any local variables that you want in the let block. So I'll talk about kind of a solution approach that I took for building the sample solution. I just want to mention the macro side of this as well. So the other part is we want to set up macros so that the user doesn't actually have to go through this process of, fun call the dispatcher and whatnot. So we're just going to introduce really simple macros that short circuit that a bit. So the first macro is going to be called set time, where you say set time and the dispatcher, so the TT for instance, and then whatever arguments you're passing. And so this is really just a macro to turn that set time into a fun call on whatever the beastie is and passing the correct symbol, the time passed symbol. So it's just rewriting that set time, and it's not a complex rewrite. It's just introducing the fun call and the correct argument to pass to the dispatcher. Similarly, we'll have a get time to look up what the current time is. So get time X and whatever spacecraft gets turned into, fun call, the dispatcher, and then it adds the current time symbol that the dispatcher is expecting. And similarly for the set speed. If I want to set a new speed for a spacecraft, it's just set speed, whatever the dispatch variable is, the name of the spacecraft and the new speed. And again, that's just getting rewritten to introduce the fun call and the correct symbol to specify we want a speed. All right, so there's a sort of skeletal versions of these macros that, of course, don't actually do anything. They just return a format statement at the moment, a print statement, pretty much. So that's the second half of this. And those macro rewrites should be pretty straightforward, but it does give you a chance to actually play with the macros a little bit. Now, obviously, there's a ton of error handling that's going to have to go into this. Right? Whenever somebody issues these commands, we've got to go through and make sure that they actually pass a valid symbol. We've got to make sure that if it's supposed to be a speed, it's actually a non-negative integer. If they specify a spacecraft, we have to make sure that it's actually in the list. So we do have to make sure that the commands that are passed are valid and respond suitably. And also that original list, right? The build time tracker has to make sure that the original list actually has valid content, that it's a string name, a string at the beginning, and then a list of pairs where each one is a string and then a non-negative integer. So there is some error checking to throw in as well. I would kind of advise getting the core functionality built first, get the macros up and running second, and then go through and start adding all of the different error checking, because you can kind of bog down into a fair bit of it here. So that would be kind of my recommended approach to things. I just want to take a couple of moments to go through and look at sort of my thoughts on what a construction would look like. So here, oops, maybe we will go through and actually resize this a little bit so you can actually see what's going on. Sounds like a plan. Okay, that might be a little better. Okay, so the idea for this is to go through and, again, we're going to set up whatever local variables we need and whatever local methods that we need in the construction function to build this dispatcher for us. So again, the local variables are the information we want to keep track of. I think this one is pretty straightforward. Obviously, we want the name for the home planet we want to record. We want to keep track of the elapsed time on the home planet, so that's going to start off as just 0. I found it easiest to throw in a constant for the speed of light, just c and set it to that 299,000 whatever. And then my approach to keeping track of the information about all of the different spacecraft was to use a hash table, where the name is a string, right? The name of each spacecraft is a string, and that's our key. And then the value you'd associate with each spacecraft would be a list, a pair of values, that spacecraft's current speed and elapsed time so far. Now, the only thing to watch out for, this is pretty straightforward use of hash tables. The only thing to watch out for is that using strings as the keys, we've got to make sure that the hash table uses an appropriate comparison method for looking at the keys. For when you say you want to look up a key value, I would advise when you create your make hash table, set it up like this. The test that I want to use for hash equivalence is the equal function. So that way you can actually compare strings in your hash keys. So, word of advice there. In terms of the local methods that I would wind up using in the in my builder here. Now, this doesn't include any of the error checking. When I went through and added the error checking to this, I added a few more things, like something that would go through that list of pairs for the spacecraft and make sure that they were all valid, and maybe some additional ones that would take a speed and make sure it was valid, or something that would take a name and make sure that it was actually in the list. So I did wind up throwing in a few more error validation functions on top of this. But for the basic structure, I found it was useful to throw in something that would print out the home planet and elapsed time, and that would print out the contents of the hash table. So it would go through all of the different spacecraft and say, okay, for spacecraft blah, its current speed is, and its elapsed time so far is, so that as I'm going through debugging, I can see what's going on. That I actually found really helpful. An initialization function, and I think I actually called it initialize, not initializer. But again, that's the one that just takes that passed parameter L and goes through and sets up all of the local variables and fills in the hash table. I set up a function to go through and say, okay, well, let's update the speed for one of the craft. So again, it just goes through the hash table, finds the right entry, and updates that. One to look up the time for a current spacecraft, again, just looking in the hash table. One to calculate the time that has, or pardon me, given the amount of time that's passed on the home planet, so if another 1,000 seconds or another 500 seconds or whatever passes, and I'm currently looking at a spacecraft that's traveling at this speed, this figures out the corresponding amount of time that's passed for that particular spacecraft. So I'm going to use this when I go through to update the times for all of the spacecraft. And then the update time function that's going to say, okay, here's a new amount of time that's passed back on the home planet. Add that to the current elapsed time for the home planet, right, that local variable we had, and go through that list of all the different spacecraft, and for each of them, run the calc time to figure out how much time that means has passed for them, and update their hash table entry. So this is going through and updating all those hash table entries. And so those were the kind of core functions that I found useful. You don't have to do it this way, but that seemed like a logical structure for me. So then in terms of implementing the rest of it, sort of after the close of our definitions of all the local functions, I ran the initialize function just to go through and say, okay, now let's set up the hash table, let's set up the values of all those variables. And actually a fair amount of error checking went in here when I added that, or calls to error checking functions. So that's just to make sure that everything's set up. And then we actually create and return the dispatch function. And this, like with most of our the examples that we've looked at so far, was essentially just a big cond that says, okay, if the command is this, then call this local method. If the command is that, then call this local method. If the command is some other thing, call this other local method. And then just a default one that says if it's anything else, it was an invalid command. So the dispatcher will actually wind up looking quite a bit like the ones that we've gone through in the examples. Most of the work we're kind of pawning off to all of these local functions that we're creating. All right, so that would be my advice for how to tackle this. And again, the issues with the macros are pretty straightforward rewrites, hopefully. All right, I will leave that with you, and we'll see how we go.